How can the crushing gravity of a dead star slow time to a crawl for one observer, while another races forward? Neutron stars are some of the strangest objects in the cosmos. Born in the fiery death throes of massive stars, they're so dense that a single teaspoon of their material would weigh billions of tons. But their mass is only part of what makes them bizarre. The real mind bender is what they do to time itself. According to Einstein's general theory of relativity, gravity isn't just a force, it's a curvature of space-time. The stronger the gravitational field, the more space and time are warped. That means near an extremely massive object, time itself runs more slowly relative to regions with weaker gravity. This is not science fiction, it's been confirmed by GPS satellites, astronauts, and atomic clocks on airplanes. But near a neutron star, this effect is pushed to the extreme, and it leads us straight into the time dilation paradox. Imagine two observers, one orbiting just outside a neutron star's surface and another floating safely far away in deep space. To the distant observer, everything happening near the neutron star seems to slow down. A clock near the star ticks sluggishly, signals arrive late. Even a falling object appears to descend in slow motion. But for the person near the star, time feels perfectly normal. Their watch ticks once per second. Their heartbeat is unchanged. It's only when they compare notes, perhaps years later, that the surreal reality becomes clear. Let's say an astronaut circles a neutron star for what feels like 1 hour. To someone on Earth or in orbit far from that star, hours or even days may have passed. The closer the astronaut is to the star's event horizon, the point of no return in a black hole, which neutron stars don't quite have, the stronger the time stretching effect. At extreme limits, it becomes so dramatic that a minute for you could be years for someone else. This isn't just a thought experiment, it's a consequence of Einstein's equations, confirmed by satellite experiments and pulsar timing. But here's the paradox. Time is supposed to be universal. It flows, ticks, and moves forward, right? And yet, near a neutron star, what counts as 1 second is different depending on where you are. The deeper you fall into the gravity well, the slower your second becomes compared to the standard second far away. This doesn't mean you're perceiving things differently. It means time itself is warped. And it gets even stranger. The light emitted from a neutron star's surface also experiences gravitational redshift. Its frequency stretches as it climbs out of the gravity well. This means even the information about time, like clock pulses or radiation patterns, gets distorted. An outside observer might detect a pulsar's radio signals and notice a slower than expected frequency, not because the pulsar has changed, but because its signals are crawling out of a deep gravitational pit. What happens if you tried to escape such an environment? As you move away from the neutron star, you accelerate into a faster time frame, but your personal history remains frozen to your experience. This is why interstellar time travel, a la science fiction, is theoretically plausible. Spending time near a strong gravitational source could catapult you into the distant future from another observer's perspective. You wouldn't age any faster or slower, but the universe around you. So what does the time dilation near neutron stars paradox reveal? That time is not absolute. It bends, flexes, and warps depending on gravity. That a second for you might not be a second for someone else. And that in the presence of extreme mass, like in neutron stars, time can be twisted so profoundly that even causality begins to blur. It challenges our everyday experience of clocks and calendars and forces us to accept a more elastic view of reality, one where space and time are stitched together by gravity itself. The time dilation paradox near neutron stars arises from the striking prediction of general relativity that time itself flows differently in the presence of extremely strong gravitational fields. Near these ultra-compact remnants of stellar collapse, neutron stars, the curvature of space-time becomes so intense that time for a nearby observer slows down dramatically relative to someone farther away. The paradox lies in how identical clocks tick at drastically different rates purely due to position in a gravitational well, making time no longer a universal experience but a local phenomenon distorted by gravity. A clock placed just above the surface of a neutron star ticks slower by several orders of magnitude than an identical clock in Earth orbit. despite both being in vacuum and far from absolute zero. It's like watching two identical movies play at the same time, one at normal speed and the other in extreme slow motion, just because it is playing deeper in a valley carved by gravity. Gravitational time dilation is a consequence of Einstein's general theory of relativity, which describes gravity not as a force, but as curvature in the fabric of space-time. In regions of stronger gravity, time stretches, slowing down for any observer located there compared to an observer farther from the gravitational source. Near neutron stars, where mass is squeezed into a radius of approximately 10K, the space-time curvature is extreme and the gravitational potential is so deep that even light must struggle to escape. On the surface of a neutron star, time can flow hundreds or even thousands of times more slowly than in Earth-based laboratories, depending on the star's mass and compactness. It's like time being pulled like taffy. The deeper into gravity's well you go, the more stretched the seconds become. This time-twisting behavior is governed by the Schwarzschild metric, a solution to Einstein's field equations that describes the space-time around a non-rotating, spherically symmetric mass. The closer you approach a neutron star's surface without crossing an event horizon, the stronger the effect becomes. What seems like a few seconds near the star could correspond to minutes, hours, or even years from an outside observer's perspective. For instance, if a spaceship orbited just above a neutron star for what felt like 1 hour to its crew, an observer on Earth might record months passing during that time. It's like walking through a fog that thickens with every step. You still move, but the world beyond fades faster than your senses can track. Gravitational time dilation plays a crucial role in our understanding of cosmic structure and evolution, affecting how we interpret signals from deep space and model stellar phenomena. It demonstrates that local complexity, the structure of a neutron star, can induce non-local distortions in information transmission and causal relationships, forcing us to rethink concepts of simultaneity, age, and duration on a cosmic scale. In pulsar timing arrays, scientists must account for time dilation when modeling signals from rotating neutron stars, or else risk misinterpreting pulse intervals and relativistic corrections. It's like listening to a ticking metronome from inside a cave. The echoing delay is not from a faulty beat, but from the cave reshaping time itself. In strong gravitational fields, not only does time slow down, but energy is redshifted as well. Photons escaping from near a neutron star lose energy, shifting to longer wavelengths. Thus, clocks near the surface are both physically ticking slower and observed to tick slower by distant observers. The gravitational redshift is direct evidence of time dilation, as energy, time, and gravity are interwoven in the extreme geometry around compact stars. The light from a neutron star is measurably redshifted, its photons emerging weaker than they were emitted, showing the cost of escaping curved space-time. It's like shouting uphill. The sound arrives, faint, delayed, and stretched, even though the voice that made it was strong and clear. From an information perspective, time dilation introduces asymmetry in data transmission, synchronization, and causality. Two observers, each equally valid in their own frame, experience different rates of information flow, meaning that events simultaneous in one frame may not be in another, complicating measurements, navigation, and even definitions of reality across gravitational gradients. A message sent from a deep space probe orbiting a neutron star will be received with delayed timestamps and slowed modulation, requiring relativistic corrections to reconstruct the original event sequence. It's like receiving a telegram in slow motion, each word stretched across minutes, not because it was typed slowly, but because space itself demands it. Gravitational time dilation is crucial to modern physics and space engineering. GPS satellites must correct for relativistic effects to maintain timing accuracy on Earth, and in astrophysics, time dilation affects how we interpret supernova light curves, gravitational wave signals, and black hole accretion models. Philosophically, it reshapes our concepts of aging, simultaneity, and travel, fueling science fiction and frontier science alike. A human explorer spending a short mission near a neutron star might return to find Earth decades older, raising questions about subjective experience, personal identity, and societal synchronization. It's like living one chapter while the rest of the world reads the entire book. Time, once thought linear, becomes relative and divergent. Though well understood mathematically, time dilation near neutron stars remains difficult to simulate or visualize intuitively. It stretches not only clocks, but our understanding of free will, cause and effect, and what it means to be present in a relativistic universe. Bridging the gap between abstract equations and real-world consequences requires cross-disciplinary insight. uniting physics, philosophy, and computation. Time dilation near neutron stars has been modeled using both general relativistic simulations and analog systems like acoustic black holes or optical slow light media. But explaining a 4D sculpture to a 3D viewer means describing shapes that cannot be directly experienced. It's like explaining a 4D sculpture to a 3D viewer. You must describe shapes that cannot be directly experienced. Future space missions may one day send probes into stable orbits near neutron stars to test time dilation effects, gravitational wave coupling, and matter behavior under extreme conditions. Understanding these environments could refine quantum gravity models, unlock new chronometric technologies, and redefine our experience of time in extended space travel. Ultimately, the paradox of time near neutron stars is not a flaw in the universe, it is a window into its deeper geometric nature. Next generation space telescopes and timing arrays will detect millisecond variations in pulsar signals caused by space-time warping, using time itself as an instrument to explore hidden physics. It's like finding that time is not a backdrop, but an instrument in the cosmic orchestra, tuned by mass, gravity, and light.